Check the correct answers below for the following statements. Statement 1. Work done by a friction force along a closed path is always zero. So this statement is actually false, and it's due to the fact that friction force is a non-conservative force. Non-conservative force, and when we calculate work done by kinetic friction, we will always see that it is negative. It will be opposing the motion. Now this particular statement is referring to a closed path. So let me illustrate this for a circular path. So for the first statement, if we have, for example, a circular path, what would happen? So on this circular path, let's say that we have radius r, this is our angle theta, and let's put this particle on a table following the circular path and coefficient of friction mu k. So we have corresponding fk. So this particle is on this circular path. So how do we calculate the work done by friction? It is minus integral 0 to 2 pi, the friction force of friction multiplied with r d theta. Why? Because if the particle moves in theta hat direction, the force of friction will be always pointing in minus theta hat direction. So this will be the force of friction. So we will see that the dot product between the force and the displacement will always be negative. So if you calculate this with a constant force of friction, mu k times the normal force, we will see that the work done is minus 2 pi r fk. So it is always negative. It's not zero. The second statement, work done by a conservative force is equal to the negative of the change in the potential energy. Well, this is actually coming from the definition of conservative force. Therefore, it is true. For a conservative force, we have F is equal to minus gradient of the potential energy, or the work done by the conservative force, force dot product with displacement integral, gives us the change in minus the change in potential energy, which is also known as a work potential energy theorem. So I can illustrate this with an example. For the second one, example, let's consider a conservative force, gravitational force. Okay, so if I have an object here that is falling a distance h to the ground level, so this is going to fall a distance h to the ground level under the influence of the gravitational force, and this is my y-axis. So the vertical axis is the y-axis. I have the gravitational force equals minus mg j hat, pointing towards the Earth. Okay, so what is the work done by the gravitational force when I go a distance h? The work done by the gravitational force, because it's a constant force, it's minus mg j hat dotted with the displacement delta y j hat. Now, what is delta y? Delta y is final position minus initial position, so it is minus h. So I will find that the work done by the gravitational force is minus mg minus h, which is mgh. Now, what is the change in the potential energy? The change in potential energy is U final minus U initial, which is 0 minus mgh. So you can see that this will be equal to minus mgh. So work done by the gravitational force will be equal to minus the change in potential energy as expected. Okay, the statement number 3. A particle is colliding with a rod on a frictionless horizontal table elastically. The rod is pivoted. So therefore, since this is an elastic collision, I should also expect that there's going to be a frictionless axle here. So we won't have any loss of energy. The linear momentum of the system consisting of the rod and the particle is conserved. Okay, so let's think about this. First of all, I want to note that because it's an elastic collision, I must have energy conservation. So if the particle has initial kinetic energy 1/2 mv initial square, this will be equal to 1/2 mv final square, plus because the rod is pivoted, it will be 1/2 the moment of inertia with respect to the pivot point rotation axis omega square. So I'm going to have kinetic energy conservation. Now, whether or not I have linear momentum conservation depends on if I have an external force acting on the system. Now, note that the system is consisting of the rod and the particle. Okay, so if I have, this is my rotation axis here. This is my rod, which is pivoted here at point P. And here is my particle coming with initial speed Vi to hit the rod. Now, if I consider the forces acting on the system, I know that there has to be a contact force R at the pivot point. Okay, so if I look at the external forces acting on the system of the rod and the particle, there is an external force R, which is the contact force at the pivot. All right, so since the net external force acting on the system is non-zero, we don't have linear momentum conservation. So therefore, this statement that the linear momentum is conserved is false. Okay. Now, in part 4, a particle is colliding with a rod on a frictionless horizontal table. The particle sticks to the rod, i.e. completely inelastic collision. The rod is pivoted again. The angular momentum of the system consisting of the rod and the particle about the pivot is conserved. Okay, so the fact that this is an inelastic collision implies that the initial kinetic energy of the particle is not equal to the final rotational kinetic energy for the total moment of inertia consisting of the rod and the particle with respect to the pivot point, omega squared. Now what I need to check for angular momentum is whether or not I have an external torque acting on the system. Now again, note that the system consists of the rod and the particle. I have this contact force here again at this pivot point, R, making an angle theta with the horizontal, let's say, and this particle comes and sticks, so it's coming with initial speed Vi. Now, since the contact force here is at the pivot point, so this is at the pivot point, it won't have any torque effect. So if I write the net external torque acting on the system, it will be 0, because the system consists of the rod and the particle. There is only the contact force which might have a torque, but it doesn't because it's at the pivot point. So this is because R at the pivot point. All right. So when we have torque, external torque acting on a system equals to 0, the angular momentum is conserved. So because remember that the net external torque is equal to dl dt, so dl dt is equal to 0. And net angular momentum is conserved. In the previous case, we had dp dt that is non-zero. So the angular momentum is conserved, therefore this is a true statement. Now the fifth statement, torque resulted from the internal forces in a system changes the total angular momentum of the system. Well, we know that the net external torque acting on a system equals to 0 implies dl dt is equal to 0 and angular momentum is conserved. So if you have internal torques, internal forces in the system that have a torque effect, these will be basically canceling out in pairs and there won't be any change in the total angular momentum. So this is not going to change the total angular momentum of the system. Therefore, this statement is false.